Hello and welcome back. Today we're going to be talking about trigonometric functions. So for the agenda, we're going to review what our objective is. Then we're going to talk about the steps for moving forward. And after that, I'll introduce the trig ratios and we'll use them in order to solve for length. So let's talk about the objective. So here the objective is to be able to solve for right triangles. So the promise of trig, if you recall from a few lessons ago, is that if we know one ratio and one side, then we have all we need in order to solve for the missing sides of any right triangle. So just to recall, let's look at this example. Given the ratio, solve for the missing sides of the right triangle. So here we're given this ratio of C and 50. It's 0.4. If I want to navigate from C to 50, all I have to do is multiply it by 0.40. Or we can also say if we want to navigate from 50 and go to C, we can do the opposite. If we can divide by 0.4. So let's go ahead and do that so we can get the value for C. So we're going to do 50 and divide that by 0.4. And here we're going to get 125. So we get that C is equal to 125. And now it's pretty much game over because we have two sides and one unknown. Whenever we have two sides and we're trying to figure out a third on a right angled triangle, we can apply Pythagorean theorem, which says that a squared plus b squared equals c squared. The sum of the legs squared, if you add them together, you're going to get the hypotenuse squared. So let's go ahead and do that. The legs are 50 and a, so we're going to keep a as a squared. But b is going to be 50 to the second power. And remember that c, that's always going to be the hypotenuse. And the hypotenuse is always across 90 degrees. So here we have 125 to the second power. All right, let's split up this equation. A squared is what we want to figure out, so that stays the same. 50 to the second power, that's 50 times 50. And then 125 to the second power, that's 125 times 125. A squared is still there, but 50 times 50, that's going to be 2,500. And then 125 times 125, that's going to be 15,625. I want to isolate a to the second power, so we got to get rid of this plus 2,500. So I'm going to do the inverse and subtract 2,500. Since we have an equality, whatever I do on the left-hand side, I have to do it to the right. So here, I'm going to subtract 2,500 as well. And then here, I get, well, nothing happens to a to the second power, so I can just drop that down. 2,500 plus, well, minus 2,500, that's 0. And on the right-hand side, I get a simplification of 1,000 or 13,125. A squared plus 0, that's a squared. And now in order to get rid of the square, I can take the square root of both sides. So square root on the left, square root on the right. The square and the square root cancel out, so I'm left with a equaling the positive length of the square root of 13,125, which is 114.56. So this is an approximation. And there we have it. So we solved for all three sides. So here we have that a is approximately equal to 114.56. B was equal to 50, and C was equal to 125. And hence we were able to accomplish what our objective was, to be able to solve for right triangles, right? So we solved for all the lengths. And to be honest, well, we kind of achieved this because we technically didn't solve for the angles, but at least we got all the lengths. Now, things got better though when we knew all the ratios, because when we knew all the ratios, now we knew all the angles, 30, 60, 90, and with the aid of the ratios, we could get the lengths as well. For example, here, if we're given one side, it's game over. We know all of the information of the triangle. This 4 is across 30 degrees, so we know that this has to be the small side. And to navigate from the small to the hypotenuse, all we have to do is multiply by 2. So 2 times 4 is 8, so the hypotenuse here is 8. And to navigate from the small side to the medium side on a 30, 60, 90, all we have to do is multiply by the root of 3. And 4 times root 3, that's going to be 4 root 3. And here we go. This time we truly were successful with our objective to be able to solve for the right triangle. Here we know everything. The same can be said for this one. In a 45, 45, 90, we have special ratios as well. And we know that here, the legs have to be congruent. So we were given a leg, and the reason we know this is because this length is across the 45-degree angle, which means that the other length that's across 45 degrees also has to be 5. And to navigate from a side to the hypotenuse, all we have to do is multiply by the square root of 2. So h is 5 root 2. And again, we've succeeded with the objective of being able to solve for right triangles. Today we want to do better. We want to improve this idea. Now we want all the ratios, not just special cases. We don't want to be able to just solve 30, 60, 90s and 45, 45, 90s. We want to solve all of them. And that's what we're leaning towards when we talk about trigonometric ratios. Now in trig, it's tradition and a convention to always use Greek letters when talking about angles. So here this is a super famous Greek letter, and it's called theta. So whenever you see that zero looking thing with a line cutting through it, that's the Greek letter theta. And it's used to describe angles, more or less. In this class, I'll use Greek letters. I'll also use regular letters such as X. But for this explanation, I'm just going to go with theta. Now, before I start talking about the trig ratios, I want to label this triangle. And here's how I'm going to label it. We're going to agree that for the angle, the given angle, whichever length is opposite of the angle that we are given, we're going to call it the opposite side. Now, we're going to look at our 90-degree angle because we're working with right triangles. So we're going to spot the 90-degree angle, and the side that's across 90 degree, that side is always going to get called the hypotenuse. The only side that remains is this one. And in a triangle, whenever you've labeled the opposite side and whenever you've labeled the hypotenuse side, the last length, we're going to call this the adjacent side. Adjacent is a very fancy word for saying next to. So this length is just next to the angle that you were given that's not the hypotenuse. But that definition is overkill. Let's just go with the one that's left for simplicity, right? The adjacent side is just the length that is left. So now we want a systematic way of calculating ratios. And let's begin by calculating the ratio of the opposite side over the hypotenuse. We have a special name for this. So whenever you want to calculate the ratio of the opposite side to the hypotenuse, we're going to call this sine. Okay, the next famous ratio we would like to calculate would be the adjacent side to the hypotenuse. And this one we're going to call it cosine, abbreviated COS. The final ratio we want to calculate would be that of the opposite side to the adjacent side. So the opposite to the adjacent, and that one also has a very famous name called tangent, abbreviated TAN. In order to apply these trigonometric functions, we're going to need to input an angle, and that's where this theta is going to come into play. So we're going to say that sine of our reference angle theta, so sine of theta, and here we know that sine, in order to calculate sine, we need the opposite side and we need the hypotenuse. So the sine of theta is going to be b divided by c, because here b is the opposite side and c is the hypotenuse. So sine of theta in our example is going to be b over c. We can do the same for cosine. So cosine of our reference angle theta, cosine by definition is the adjacent over the hypotenuse. The adjacent side is a, our hypotenuse is c, so cosine of theta is going to be a over c. Lastly, we can calculate tangent. Tangent of theta, and tangent by definition is the opposite side over the adjacent side. So here we're going to grab b, our opposite side, and divide it by a, the adjacent side. So tangent of theta is b over a. Now here are the takeaways. So the takeaways are, first, the angle of reference. That is going to be the angle that is given. Now it's never going to be 90 degrees. In this case it was theta. Next, we have three sides. The opposite side is always going to be across the angle of reference. The hypotenuse is always going to be across a 90-degree angle. And the adjacent side, that's going to be the remaining length. And now here's a very useful acronym, SOHCAHTOA. So use this in order to help you remember the ratios. So here, for example, SOH, the S is going to stand for sine. And you know that in order to solve for sine of theta, you're going to have to get the opposite and divide it by the hypotenuse. The next one, Ka, that stands for, the C stands for cosine. And cosine of theta, in order to calculate that, you're going to get the adjacent side and divide it by the hypotenuse. So A over H. And then finally, we get tangent, we get TOA. The T stands for tan, and tangent of theta is going to equal the ratio of opposite over adjacent. So we get O over A. This acronym is super helpful, and let's see an example. Example 1, we have to find the three trigonometric ratios of sine theta, cosine theta, and tangent theta. To do this problem, I'm first going to label my triangle. So I look and I see that theta is my angle of reference. So I'm going to begin labeling it by labeling the opposite side, which is always going to be the length across the angle of reference. If I check out my 90-degree angle, the length across 90 degrees, that's going to be the hypotenuse. And then, by process of elimination, the remaining length is called the adjacent side. So let's calculate sine of theta. So let's bring out SOHCAHTOA. And SOH, that's sine. So sine of theta is going to be the opposite over the hypotenuse. And here my opposite side is 5. My hypotenuse is root 26. So we get 5 over root 26. Let's get cosine now. Cosine of theta, we know that that's going to be the ratio of adjacent over hypotenuse, A over H. So A is 1 and the hypotenuse is root 26. So cosine of theta is 1 over root 26. Finally, we're going to get tangent. And tangent, by definition, is the ratio of opposite over adjacent. So tangent of theta is going to equal O over A, and here my opposite side is 5, my adjacent side is 1, so here we get 5 over 1, which is just 5. Go ahead, try the next set of examples, and when we come back, I'll show you how to use trig ratios in order to find missing lengths.